What we're looking at here is the first few steps in proving the power rule for derivatives. So I started with positive integer powers because they're typically the easiest things to work with. As we'll see when we go through this, negative integer powers are an easy enough extension of this, and fraction powers are another story, but we start with these. So I started with the smallest power of x that is not covered by the linear function rule, x squared. So the derivative of x squared put into the limit definition of the derivative. Now, this is really the big key here. The expansion of x plus h to whatever power. So what I did is we'll look at all the steps of this, but I also set up the beginning of the derivative of x cubed, where again we see x plus h to that power. And I set up down here the derivative of x to the fourth, where we again see in the limit definition x plus h to the fourth power. So the first and really most important key step of this is the expansion of x plus h to the power. Now, it's not as simple as just doing x squared plus h squared. We actually have to write x plus h once for each, so that there are n factors of it where n is the power. So x plus h squared is x plus h times a second x plus h. So we have to employ a FOIL technique, or whatever name you use for the multiplication of polynomials. So x plus h squared expands to x squared plus 2xh plus h squared. And we're going to see something happen here that we saw happen previously in dealing with the limit definition of the derivative. Namely that in a polynomial function, all of the terms that do not have an h are going to cancel out, leaving us with only terms that do have h's. So once those x squared terms are gone from the numerator, we have this, and from here we can factor an h out of the numerator. And that is going to fix our problem of having h in the denominator. Because as h approaches 0, of course, we get a discontinuity in our expression. So we get ourselves down to just the limit as h approaches 0 of 2x plus h, and we substitute 0 for h finally, and we get 2x. And that is in keeping with the power rule that was stated in the PowerPoint. But again, the key here is going to be in the expansion of the x plus h to the power. The rest of this is, as I mentioned, things that we've seen in previous dealings with the limit definition of the derivative, namely that all the terms without an h have disappeared from the numerator. Now, granted, we've dealt with polynomial functions almost exclusively so far, so this is not something that we can expect to have happen in every single function that we differentiate ever, but with polynomials, this is what happens every time. In the numerator, the terms without h cancel out. If, therefore, all of the remaining terms have an h, we can factor the h out to simplify with the h in the denominator. Now, the point is that the two terms that are left here in the simplified expression are directly related to these two terms in the expansion of x plus h squared. Now, the fact that there's two terms is due to the fact that it's the derivative of x squared. Down here, and again, I did not work through the entirety of the problem based on the idea that, again, if the x terms are going to cancel and the remaining terms have an h that can be factored out, then really what we need to be focusing on is the expansion of the binomial. So here we have x plus h cubed, and it results in x cubed plus 3x squared h plus 3x h squared plus h cubed. Again, this can be obtained by taking 3 factors of x plus h and multiplying them together. First, the first two, and then that product times the third. Now again, what we see here is the x cubes will cancel out. The remaining terms then all have at least one h in each of them, and that h can be factored out to cancel with the 1 in the denominator. So I'm going to combine a step or two here. Since we have the visual aid of looking at those 3 things, I'm going to take the common h out of each of them, leaving me with 3x squared plus 3x, and with one factor of h gone, there remains a factor of h in that term. And from h cubed, with one factor of h removed, that leaves 2 remaining. And what we're left with is the limit as h approaches 0 of the expression 3x squared plus 3xh plus h squared. Here's the thing to note, of course. The second that h disappears from the denominator, we've removed the discontinuity that prevented us from substituting 0 for h. But if we substitute 0 in for h, every term that maintains an h at this step will drop out, much as we saw up here. The only term that will be left then, after doing this, will be the very first term in this remaining expression, which is the second term of the expansion with its h removed. Remember, the first term of the expansion will have no h's and will cancel with the term over here every time. And if the remaining terms all have h's and we take one h out, each successive term will have h's remaining even after one has been removed. And those remaining h's will cause these terms to become 0 when we substitute 0 in for h. The only term that will remain is this second term of the expansion without its h. So before we come down here to the derivative of x to the fourth, I want to talk more about the expansion of the binomial. There's actually a thing called the binomial expansion theorem, because this kind of thing is actually rather relevant and shows up a surprising amount. So, what we're going to look at here is the expansion of the binomial x plus h to a power of n. Now, usually the binomial expansion theorem is done with the binomial a plus b to the power of n, but since we're going to be using x plus h in our derivative formula, I just chose to use those letters instead. Now, the whole idea, of course, as we saw before, is that the expanded form requires n factors of x plus h. Now, usually you can't multiply more than 2 things at a time unless you're a little creative about it. If you actually were to work through all of the multiplications that occur in here, what it basically comes down to is that each term of each polynomial has to be multiplied by each term of every other polynomial. Now that sounds like an awful lot of things to do at once. Let me repeat that. Each term of each polynomial has to be multiplied by each term of every other polynomial. Basically what it comes down to is this. I have to choose a factor, either x or h, from the first polynomial, and then a factor of either x or h from the second, and then a factor of either x or h from the third. And there are many combinations that I can choose. Let's start with the simplest. I can choose x from the first, and x from the second, and x from the third. And in this way, I get x cubed with no h's. Now, it is possible, of course, to choose x from two of them and h from the third. But there is more than one way we can do that. We can literally choose x from the first two and h from the third, but we could also choose x from the first and third and h from the middle. Or we could choose h from the first and x from the other two. So there's multiple ways to choose that, but regardless of how many ways there are, we get a term that's going to have two factors of x, but only one factor of h, because if I can't do all three x's, I already covered that. I have no choice but to choose at least one of them to be an h. Of course, I could pick two of them to be an h, but if two of them are chosen to be h, that means the third has to be chosen to be x. And of course, the last part, what if all three are chosen to be h? Now, what we get here is that no matter what, I'm picking three factors every time. Either all three are x, or I take out one x to use an h instead, or I take out a second x to use a second h, or I take out all three x's to use all three h's. This is every combination of ways that I can choose the factors from to multiply together from these three binomials. In general, what we have then is that x plus h to the n, with its n factors, can work like this. I can choose all n factors to be the first term x. Or I can choose all but one of them as x, and the last one as h. Or perhaps I can choose all but two of them as x, because the other two are h's, and so on down the line, until eventually I get to a point where I am choosing only two of them to be x, which means all the other factors have to be h. And then a single x with all other factors being h. And finally, all of the factors are h. Now, of course, when you multiply out a polynomial, or any number of polynomials, there are coefficients on the terms. The coefficients are the interesting part. There are several different ways to go about them, but perhaps the most basic, and for us it will actually suit our purposes best to look at it this way, is to use something called Pascal's triangle. Many of you have very likely seen this before, even if you don't recall it by name off the top of your head. It works like this, that we have a pyramid, essentially, where the outer rows of the triangle will always be 1. And then for each new spot in the interior, it is the sum of the two values just above and to the left and just above and to the right. So in the next row, we'd have, again, 1s on the outsides, and then this spot here would be 1 plus 2, 2 plus 1. Note the symmetrical nature of this, just by the way. In the next row, 1 on each end. In the middle, we would have 1 plus 3 is 4, 3 plus 3 is 6, and 3 plus 1 is 4. Again, very symmetrical, which I hope should make sense, just the very nature of this. We'll do one more here just to kind of get the feel for it down. Again, 1's on the outer edges, and then 1 plus 4 is 5, 4 plus 6 is 10, 6 plus 4 also 10, and 4 plus 1 is 5 again. Now, some of these might actually seem familiar if you go back and look at it. this is the expansion of x plus h squared. And note that the coefficients here are 1, 2, and 1. The same as the values in this row of Pascal's triangle. Actually, the values in the nth row of Pascal's triangle are the coefficients of the expansion. So depending on what the power of n is, we go to that row, and those are the coefficients. Note that the first term always has a coefficient of 1 because there is only one way to actually choose all three factors to be x. Remember when we talked about the x squared times h though? How many ways were there to select x from 2 of them and h from the third? Well, we could do x from the first 2 with h from the third. That's 1. We could choose x from the first and third, but h from the middle. That's 2. We could choose h from the first one and x from the second and third. That's 3. And sure enough, for a power of 3, the coefficient of the second term of the expansion is 3. We get a similar situation here. We can choose x from the first and h from the other 2, x from the second and h from the other 2, x from the third and h from the other 2. So there are, again, 3 ways to do that. And lastly, all 3 of them being h's. Well, h, h, and h. There's no other way to do that. So again, a coefficient of 1, which we don't typically write in the expansion, of course. Now, back to the derivative of x to the fourth here. You can see I've already done the expansion in exactly the way that the binomial expansion theorem says I should. All 4 factors of x, 3 factors of x with 1 factor of h, switch out a second x, so now I only have 2 x's, but I have 2 h's. Switch out another factor of x, I'm down to a single x, but I've gained an h to replace it. And lastly, lose the last x, and now they're all h's. And of course, the minus x to the fourth here on the tail end. Now, the coefficients are 1, 4, 6, 4, 1, as corresponds to Pascal's triangle for n equals 4. Now let's come back up here for a moment and see what happened with these two smaller powers, x squared and x cubed. What we said was that the first term of the expansion is going to cancel out with the subtraction at the other end there. So once again down here, our x to the fourth will cancel out with minus x to the fourth. All of the remaining terms then all have an h in it. By the very nature of the binomial expansion, the only term that had no h was the very, very first term of the expansion when all of the factors chosen were x's. Of the remaining terms, they all have at least one h that then gets factored out in the next step. So that the removed factor of h can simplify out with the factor of h in the denominator and thus fix the discontinuity. But look at what we're left with again. The next step is to take this expression that no longer has the discontinuity by having the h in the denominator and substitute 0 in for h, where again, each term that still has an h will then get a times 0 in it and drop out. And what will we be left with? This term. That term always corresponds to this term in the expansion. The second term of the expansion. Because remember, the first one will cancel out in the numerator of the derivative. So if this is the next one in line, and its h gets factored out, there is our x to the n minus 1, one smaller power than what we began with. The coefficient of this term is always the second number in Pascal's triangle, which by its very nature will always take the 2 and the 1 and add it and get 3. And then 3 plus 1 is 4. 4 plus 1 is 5. 5 plus 1 is 6. So the coefficient of that term is always the value of n. Now, the other terms have coefficients, yes, but in the derivative, all of them will cancel out. This cancels out of the numerator. These other ones will cancel out after we factor out our h. And the only thing we're left with every time is n times x to the n minus 1. And that is exactly the power rule for derivatives. Now, the advantage of the video, of course, you get to go back and watch this again, now that you know where I'm headed with it, and see how it developed all over again. And the second time around, it should definitely make more sense, I think. Now, as for negative powers, it's actually not that difficult. Negative powers follow very similarly. Allow me to show you at least the beginning stages of it. By the limit definition, this would be the limit as h approaches 0 of x plus h to the negative 2 minus x to the negative 2 all over h. Now, we have a small adjustment to make before we proceed with the binomial expansion, which we can't do because the binomial expansion is based on a positive integer power. This is obviously a negative. But that's okay because we don't really ever deal with negative powers per se. We almost always convert them back into a positive power by reciprocating the base. So we can rewrite this as 1 over x plus h to the positive 2 minus 1 over x to the positive 2 all over h. So as you can see here, we get the x plus h squared. So even though it's to a negative power, at some point we're still going to be making use of the expansion of x plus h to the second power. If this was x to the negative 3, we'd have x plus h to the third in the denominator. So negative powers are going to end up working very, very much the same way that positive powers did, in the sense that, well, we're going to have to convert them to positive powers. Again, we have an extra little hiccup here, and that's that in order to make this useful, before we expand the x plus h squared, we have to subtract the two fractions in the numerator, which means we need to get them a common denominator. So we multiply the second fraction by x plus h squared so that they both have an x plus h squared in the denominator. But this one has an x squared, so we will need to multiply the first fraction, top and bottom, by x squared. So we now have x squared over x squared times x plus h squared. minus x plus h squared over x squared times x plus h squared. And that whole thing over h. This looks horrifying, yes, but if we only focus on the parts we need to at the moment, like, yes, this is a large complex fraction, but this h in the big denominator is not something we need to be worried about just at this point. We're writing it, yes, but it's not something that's involved to this point. So we'll try and ignore that and focus on what we're dealing with in these two fractions in the numerator, which now have the same denominator, and it allows us to combine it into a single fraction in the numerator. So we have the big fraction, which has an h down there, and the numerator has now become a single fraction, x squared minus x plus h squared over x squared times x plus h squared. Note that what we have here in this combined numerator is the same thing in reverse. It is the same two terms being subtracted in the opposite order from what we had in the derivative for x to the positive 2. So we're going to see the same expansion. We're going to see the same terms canceling out. We're going to see an h factor out. The only real difference here is that because the subtraction's in the other order, we're going to end up with exactly the opposite sign answers plus a denominator. Now, actually, because this is a complex fraction, the best way to deal with this would be, instead of writing a big division by h, write a multiplication by its reciprocal, 1 over h. So there's our factor of h in the denominator. We know what the expansion of this will look like from when we did it for the derivative of x to the positive 2. So we will get the terms without an h canceling out. The remaining terms will all have at least one h. Factor it out to cancel with this. So we're going to see, really, these parts of it right here, the x squared minus x plus h squared, is the reverse of the subtraction that we saw for the derivative of x to the positive 2. And the h in the denominator off to the side over here. So the only differences are, again, the reversal of the subtraction in the numerator will cause the remaining terms to come out to be negative, to have the opposite signs. Otherwise, this will work exactly the same way with this denominator, which this part actually is not a problem. We can substitute 0 in for h here, and everything will be just fine. It's this h which causes the problem. So since we already know that's going to cancel out, and I leave that to you to work through, but since we already know that's going to cancel out, it's not a problem. So if you work through this the rest of the way, you will get to a result that does reflect exactly what the power rule would tell you to do if we had just left it in its original form. Let's finish that out. So we have x squared, and then the expansion here will become x squared plus 2xh plus h squared all over x squared times x plus h squared times h. Now don't forget the subtraction has to distribute, but the x terms will cancel out. So what we'll be left with is, as I mentioned, the exact opposite of the terms that we had when we did this with x to the positive 2. Now, taking a little bit of a liberty here, if I factor a single factor of h out of each term of the numerator, that will then factor with the simplify with the factor of h that's in the denominator. And what we would be left with would be the limit as h approaches 0 of negative 2x minus h over x squared times x plus h squared. And at this point, as I said, this factor, there's nothing wrong with sticking a 0 in for h there. And of course, in the numerator, there's never a problem. So we get negative 2x. The h here will drop out because minus 0 is 0. And x plus 0 is just x. So we have in the denominator this x squared times another x squared, which is x to the fourth. A single factor of x cancels from both the numerator and denominator and leaves us with negative 2 over x cubed. Now, because the power rule required us to write it as x to a power, implication being it is in the numerator, it's better to actually write a negative exponent in the numerator than a positive exponent in the denominator as far as the power rule is concerned. So we could then rewrite this as negative 2x to the negative 3. Now, algebraically, this might be the proper way to write it, but this is the way that's going to help us see the relationship of the power rule. The power, negative 2, comes down in front and becomes the coefficient, which we see down here. And then we subtract 1 from the power. Negative 2 minus 1 is negative 3. So I hope that from this it's not necessary to go through the derivative of x to the negative 3, but you certainly can. It's not a huge deal to do so. I hope that what you can see here is that you would end up seeing a lot of the same things that happened in the derivative of x to the positive 3 would happen again in the derivative of x to the negative 3. A few extra considerations. Finding the common denominator. The subtraction is reversed. That causes us to have opposite terms later on. And lastly, we will have a denominator, and there will be some resolution necessary between the remaining term in the numerator with the power of x that's in the denominator. But all told, it should come down to exactly what the power rule says it should.